articles, research notes.
Yeah, and pull out the key stuff.
Exactly.
Yeah.
Sort of a shortcut to getting up to speed. And today, we're diving into, well, maybe the biggest puzzle in physics.
It's certainly up there. Been baffling people for, what, nearly 100 years now?
Right, this huge split in how we see the universe.
You've got general relativity, Einstein's picture, big stuff, stars, galaxies, all smooth and predictable, deterministic even.
And then you flip to the quantum side.
Exactly, the super tiny world, atoms, particles, and it's all just weird. Probabilities, jumps, not smooth at all, inherently uncertain.
Two amazing theories, incredibly successful in their own domains, but they just don't play nice together.
Not at all. Try to quantize gravity, make it fit the quantum rules like the other forces.
The math breaks.
Completely. You hit these brick walls, these infinities that just scream error. It's like the theories are speaking different languages, fundamentally.
Yeah.
It tells you something crucial is missing,
This conceptual chasm, as you put it. So the research we've looked at points towards a really radical idea, doesn't it?
It really does. What if? What if gravity isn't fundamental?
Not one of the building blocks, but something that emerges.
Exactly. Like wetness emerges from water molecules, but isn't a property of a single molecule. Gravity could be like that, emerging from something even deeper.
And that deeper thing, that's where "if" from Qubit comes in.
Precisely. It reframes the whole problem. Instead of forcing gravity into quantum mechanics, maybe we should look at quantum information, entanglement, computation.
And see if gravity, even space-time itself, pops out from that.
That's the core idea, and that's what we're going to unpack in this deep dive. The thesis is that space-time geometry, the very fabric of the universe, emerges from how quantum bits or qubits are entangled.
And we'll get into things like the holographic principle, ADS-CFT, and this wild idea that it all works like a quantum error-correcting code.
Making the universe surprisingly robust, it's a fascinating journey, really challenges how you think about reality.
Okay, let's start that journey. Where do we begin? Black holes seem like a good, mysterious starting point for thinking about gravity and information.
Definitely. Classically, from Einstein, they're pretty simple, just super dense objects, points of no return.
Nothing escapes, not even light. Simple, right?
Too simple, it turned out. Then came the quantum twist. Jacob Bekenstein, back in the 70s, he had this revolutionary idea.
That black holes have entropy.
Yeah. Which was crazy because entropy implies information, complexity, internal states. It means black holes aren't just featureless voids.
And Stephen Hawking backed this up, showing they radiate. Hawking radiation.
He did. He showed they have a temperature and radio particles, confirming Bekenstein's hunch mathematically. It meant black holes obey thermodynamic laws, sort of.
But the really weird part, digging into those formulas, was about how much entropy they have, wasn't it?
Oh, absolutely mind-bending. For normal stuff, like a box of gas, entropy scales with the volume, right?
Right.
More space, more possible arrangement.
Makes sense.
But for a black hole, the Bekenstein-Hawking entropy is proportional to the surface area of its event horizon, the area.
Not the volume inside, just the boundary surface.
Exactly. That was the first massive clue. It suggested that somehow all the information needed to describe what's inside a gravitational region is encoded on its boundary.
Which sounds holographic.
Right.
Like a 2D surface holding all the info for a 3D volume.
Precisely. That area law was so strange it led Gerard Hooft and Leonard Susskind to propose the holographic principle. Maybe the entire universe works like that. Maybe our 3D reality is just a projection from some lower dimensional boundary.
Okay, that's a huge leap. How do we make that concrete? How do physicists actually work with this holographic idea?
That brings us to the AD-SCFT correspondence. This is where the holographic principle gets really precise, like a mathematical dictionary.
All right, break that down. AD-SCFT. What are the players?
Okay, so first you have anti-de Sitter space, or ADS. It's a specific kind of space-time geometry. Forget the details. Just picture it like a theoretical bottle or a can. It has an interior, the bulk, and importantly, it has a boundary surface.
A boundary with one less dimension than the inside, the bulk.
Exactly.
Yeah.
Like the label on the can is 2D, but the inside is 3D. Or a 5D ADS bulk has a 4D boundary.
Got it. And CFT.
That stands for Conformal Field Theory. It's a type of quantum field theory, but a special one that lives only on that boundary. It doesn't have gravity, crucially, and has special symmetries. It looks the same at all scales.
So you have gravity theory in the bulk,
Yep.
ADS, and a quantum theory without gravity on the boundary, CFT.
Right. And then Juan Malsena in 1997 proposed something stunning. He said these two seemingly different theories are exactly equivalent. They're dual descriptions of the same underlying physics.
Equivalent, like completely interchangeable.
Mathematically, yes. It's a duality. Anything happening in the ADS bulk has a precise counterpart in the boundary, CFT, and vice versa. It's this holographic dictionary.
Wow. Can you give an example from the dictionary?
Sure. A really key one is the radial direction in ADIS, how deep you go into the bulk, away from the boundary. That corresponds directly to the energy scale, or resolution, you're looking at in the boundary CFT. Going deeper in the bulk is like zooming out on the boundary.
Okay, that connects geometry and energy scales.
Yeah.
What else?
Well, another incredibly important entry involves quantum entanglement on the boundary. The amount of entanglement between two regions on the boundary is related to the area of a specific minimal surface in the ADS bulk that connects those two regions. That's the Ryu-Takayanagi formula, which is profound.
Entanglement equals area. We'll definitely need to come back to that. But this duality, it lets you translate hard problems into easier ones.
That's the magic. It's often a strong-weak duality. When the quantum theory on the boundary, CFT, is strongly interacting and impossible to calculate.
The gravity theory and the bulk, ADS, might be weakly coupled, described by classical Einstein gravity, which is much easier.
Exactly. You can solve the easy gravity problem and then translate the answer back using the dictionary to learn about the hard quantum system. It's an incredibly powerful tool.
Okay, so this holographic dictionary links gravity and geometry in the bulk to quantum stuff, especially entanglement on the boundary. But entanglement, isn't it notoriously fragile?
That's the million-dollar question, isn't it? Quantum states are incredibly delicate.
Right. We hear about quantum computers needing extreme isolation because any little interaction with the outside world decoherence just destroys the quantum information.
And you can't just copy quantum information to make backups. Because of the no-cloning theorem, measuring it also collapses the state. So how could something so fragile possibly build something as robust and stable as space-time?
It seems like a major paradox. How do you protect this information?
Well, this is where a completely different field, quantum computing, provides a crucial insight. Quantum error correction, or QEC.
So the techniques designed to build stable quantum computers might actually be how the universe protects space-time itself.
That's the mind-blowing connection people started making. The challenge for quantum computing was precisely this fragility. How do you compute if your qubits keep losing their information?
So how does QEC work if you can't copy or directly measure the state?
The breakthrough from people like Peter Shor and Andrew Steen in the mid-90s was to use entanglement itself as the shield.
Use the fragility to fight the fragility.
How? Instead of storing your important quantum information, your logical qubit, in a single physical qubit, you encode it across many physical qubits using a very complex, highly entangled state. You spread the information out non-locally.
So if one physical qubit gets messed up by noise,
the logical information being distributed across the whole network of qubits is likely still safe. The error only affects a small part of the whole encoded state.
Okay, but how do you find and fix the error without measuring the logical information directly?
That's the clever part. You design the code so you can measure certain collective properties of the physical qubits. These measurements don't tell you anything about the stored logical information itself, but they do reveal if an error occurred, and often what kind of error it was, like a bit flip or a phase flip.
That gives you an error syndrome.
Exactly. The syndrome tells you what went wrong, and then you can apply a specific correction operation to fix it, all without ever learning or disturbing the precious logical qubit.
It's all about redundancy and this non-local encoding. The information isn't here or there, it's everywhere in the code.
That non-locality and redundancy are absolutely key. Keep that in mind, because it's exactly what seems to be happening with space-time in ADS-CFT.
Okay, so let's make that connection explicit. How does ADS-CFT relate to quantum error correction? This feels like the core synthesis.
It really is. There was this puzzle that researchers were bumping up against. In ADS-CFT, you had this property called bulk locality. If I do an experiment deep inside the ADS bulk, causality says it shouldn't instantaneously affect something far away on the boundary, right? Effects can't travel faster than light.
Standard physics.
But the holographic dictionary also seemed to say that you could represent that same local operator deep in the bulk by using operators acting on different disconnected regions of the boundary CFT.
Wait, the same piece of information, the state deep inside, could be reconstructed from boundary region A or from a completely separate boundary region B.
Exactly, which sounds like you're cloning quantum information. How can the same information be in two different places? It seemed to violate basic quantum rules.
Okay, yeah, that's a serious paradox. How do you resolve that?
The resolution came in 2014 from Amheri, Dong, and Harlow ADH. Their proposal was stunningly simple yet profound, they said. ADA CFT isn't just like a quantum error-correcting pund, it is one.
Whoa! So the whole duality is the error correction.
Yes. In their interpretation, the quantum state space of the boundary CFT, all its possible states, that's like the space of the physical qubits. And the states in the bulk that correspond to smooth classical gravity, the low-energy states, those are the protected logical qubits. The holographic dictionary itself is the encoding map.
So the weirdness of reconstructing bulk info from different boundary regions
Isn't a paradox at all. It's a standard feature of quantum error correction called sub-region duality or entanglement wedge reconstruction. It just means the logical information in the bulk is robustly encoded. You can lose access to part of the boundary, physical qubits, and still recover the information from another part.
So the robustness of space-time, its classical appearance, is because it's built on this incredibly robust error-correcting code structure provided by entanglement.
That's the idea. The very structure of the holographic map ensures that local information deep inside the bulk is protected against local erasures or errors on the boundary.
So where do black holes fit into this QEC picture then? Are they like overwhelming errors?
That's a great way to think about it. The QEC interpretation works beautifully for the code subspace, the states corresponding to nice, smooth, low-energy geometries in the bulk.
Like empty ADS or ADS with a few particles.
Right. But if you try to encode too much energy or information, if you, say, throw so much stuff into the bulk that it collapses into a large black hole,
Then what happens?
the state becomes too complex, too energetic, it falls outside that protected code subspace, the error correction fails, the system gets overwhelmed.
And the nice, smooth local description of space-time breaks down.
Exactly. You can no longer describe what's happening using local operators in a classical geometry. The emergence of space-time fails. So black holes, in this view, mark the boundary, the limits, of where this particular quantum error code works effectively.
That's fascinating. It ties black holes directly to the limits of emergent space-time. But it's still quite abstract. Are there simpler models, toy models, that let us see this QEC structure more clearly?
Yes, absolutely. And that's where tensor networks have become incredibly useful.
Tensor networks, these are like diagrams.
Yeah, they're basically graphical tools physicists use to represent and calculate properties of very complex quantum states, especially their entanglement patterns. Nodes represent tensors, lines connecting them represent entanglement.
Okay. And how do they help visualize emergent space-time?
Well, there's a specific type called MEMRA, multi-scale entanglement, renormalization, and sets. It's structured in layers.
Layers, like building something up.
Kind of. It's designed to efficiently represent the ground states of CFTs, the kind of theories living on the boundary in ADA CFT. It works by systematically removing short-range entanglement layer by layer.
Okay, so what's the geometry connection?
This was Brian Swingle's amazing insight around 2009. He noticed that the structure of this mirror network, the way the tensors are connected layer by layer, it geometrically resembles a discretized version of hyperbolic space.
Hyperbolic space.
Yeah.
Like the geometry of ADS.
Exactly. The layers in the mirror network naturally correspond to the radial dimension in ADS, the direction going into the bulk. So the tensor network, purely from its entanglement structure, was basically building the curved geometry and the extra dimension of the holographic bulk.
Wow, so geometry literally emerges from the entanglement pattern.
It was a huge visual confirmation of the idea. And then building on this came models like the Happy Code, named after the authors Pestowski, Yoshida, Harlow, and Preskill. It's an explicit toy model of holographic quantum error correction using specific building blocks called perfect tensors arranged in a hyperbolic tiling.
Like tiling a Pringles chip, sort of.
Right, sort of, yeah. And this Happy Code explicitly demonstrates the QEC properties. You can see how a logical operator placed deep inside the network, the bulk, can be represented by operators on different segments of the boundary, just like an ADAS CFT. It shows subregion duality in action.
And it connects to entanglement entropy, too.
Yes. It gives a discrete version of the Ryu-Takayanagi formula. The entanglement between a boundary region and the rest is related to the minimum number of connections, like a minimal cut you need to make in the network to separate that region, which is like a geodesic length in the bulk geometry.
So these toy models, while simplified, really capture the essence space-time geometry and gravity emerging from quantum entanglement structured as an error-correcting code.
Precisely. They strip away the complexities of string theory and show the underlying quantum information architecture.
Which brings us full circle to it from Qubit, space-time from entanglement.
Mhm.
Let's revisit that Ryu-Takayanagi formula, entanglement equals area. That seems central.
It really is perhaps the most concrete and profound piece of the holographic dictionary. Proposed in 2006, later generalized, it says the entanglement entropy of a boundary region is equal to the area of the minimal surface in the bulk that ends on the edge of that region, divided by 4 times Newton's constant in Planck units.
So it's not just related, it's equal. A purely quantum information quantity, entanglement entropy.
Wow. Is literally calculated by a purely geometric quantity area in the emergent spacetime.
It just weaves them together inextricably. More entanglement on the boundary means more area in the bulk.
It's like the threads of entanglement are literally weaving the fabric of space. The geometry is a reflection of the entanglement structure.
Okay, so entanglement builds area. What about connections? Wormholes.
Ah, yes. EPR, another mind-bending conjecture, this one from Maldacena and Susskind in 2013.
Year Einstein-Rosen bridge, a wormhole. EPR, Einstein-Rafalski-Rosen pair, entangled particles.
Exactly. Their conjecture is that these two concepts are, in some deep sense, the same thing. If you have two maximally entangled systems, EPR.
They are geometrically connected by a non-traversable wormhole, ER bridge.
Right. So that spooky action at a distance that bothered Einstein so much about entanglement.
Yeah.
Maybe it's not so spooky. Maybe it's just geometry. Creating entanglement between particles is like literally stitching a tiny wormhole connection between them in the underlying fabric of spacetime.
So the connectivity of space itself isn't fixed. It depends on entanglement.
That's the radical implication. Entanglement doesn't just correlate distant things. It connects them geometrically at the Planck scale.
So putting all this together, space-time isn't the stage. It's not fundamental.
It seems not. The truly fundamental reality in this picture might be this vast, abstract quantum state space, the Hilbert space, associated with some boundary degrees of freedom, some qubits.
And our familiar space-time, with distance, curves, gravity, that's all just an emergent, approximate, large-scale description.
A coarse-grained view, yeah. Like how temperature and pressure emerge from the collective behavior of zillions of atoms, but don't make sense for a single atom. Spacetime and gravity might emerge from the collective statistical mechanics of entanglement.
So let's recap the big picture from this deep dive. The universe looks classical and robust.
That's because it's fundamentally built on quantum error correction principles. Spacetime is emergent, and it's fault-tolerant by design thanks to entanglement.
And this framework seems to offer a powerful new way to tackle old problems, like the black hole information paradox.
Absolutely. This has been one of the biggest triumphs recently, using quantum-corrected versions of the Ryu-Takayanagi formula, incorporating ideas from QEC, like quantum extremal surfaces, and islands.
Islands?
Yeah, basically realizing that when calculating the entropy of Hawking radiation far from the black hole, you sometimes need to include a region inside the black hole, an island, as being part of the system entangled with the radiation.
Okay. And do that.
Doing that, the calculations suddenly match the expected page curve. This curve describes how the entanglement entropy of the radiation should first rise and then fall as the black hole evaporates, indicating information is preserved, not lost. Getting this curve right was a huge breakthrough.
Powerful validation for this whole it from Qubit, QEC, holographic approach.
It really feels like we're on the right track. But of course, there are still huge challenges.
It's not all solved yet.
Oh, definitely not. These ADA-CFT models are amazing, but ADS space isn't quite our universe. Our universe seems to be expanding, described by de Sitter space with positive curvature, not negative like ADS.
So extending these ideas to de Sitter space is a major hurdle.
A huge one. Also, most calculations rely on simplifying assumptions like a large number of quantum fields, the large N limit. Understanding what happens beyond that limit, getting to more realistic quantum gravity effects, is tough.
And bridging the gap from toy models like Happy to real complex gravity.
Exactly. And there are still deep questions. What exactly is the mechanism for information escaping a black hole? What's the holographic description of the singularity inside? Can we even dream of testing any of this experimentally?
Maybe with quantum simulations or incredibly precise measurements.
People are definitely exploring those avenues, building complex, entangled states in labs that mimic these holographic QEC codes, looking for tiny quantum gravity signatures. It's a very active frontier. Lots of research, new codes, new software being developed. It feels like progress is accelerating.
Which leads us to our final provocative thought for you today. If this perspective is right, if space-time emerges from entangled qubits, operating like a quantum error-correcting code,
Then the universe, in a very real sense, is a quantum computer.
the laws of physics are its operating system, the software.
And space-time, matter, everything we see is the emergent output, the data structure generated by the underlying quantum computation.
It completely reframes everything, not just physics and cosmology, but maybe even our understanding of what reality is.
It's a truly profound shift in perspective. Makes you wonder what else might be emergent.
Absolutely. A lot to ponder there. Thank you for joining us on this deep dive into It from Qubit and the idea of space-time as a quantum error-correcting code.
Hope you found it as fascinating as we do.
We hope you leave with a new way of thinking about the fabric of your reality. Until next time.